Deep neural networks have revolutionized artificial intelligence, driving breakthroughs in computer vision, natural language processing, autonomous systems, and scientific discovery. But despite their remarkable performance, they remain deeply vulnerable to tiny, imperceptible input perturbations. A single pixel change, a sticker on a stop sign, or even camera noise can cause a self-driving car's perception system to misclassify a critical object, potentially leading to catastrophic failures. This isn't just a theoretical concern. It's a real-world threat to safety-critical applications like robotic surgery, medical diagnostics, and autonomous vehicles. The core issue: neural networks learn decision boundaries that are highly sensitive to small input changes, what researchers call adversarial vulnerability. These vulnerabilities expose a fundamental gap. High accuracy does not imply robustness. So how do we ensure that a neural network will behave correctly not just on clean data, but also under realistic perturbations? This is the central challenge of robustness verification, the task of providing mathematical guarantees that a network's predictions remain unchanged within a bounded region around a given input. For decades, classical verification methods, like SMT solvers, branch-and-bound algorithms, and mixed-integer programming, have been used to certify robustness. These techniques work well for networks with ReLU activation functions, thanks to ReLU's simple piecewise linear structure. Negative inputs are 0, positive ones pass through unchanged. This binary behavior allows for efficient constraint-based reasoning and reachability analysis. But here's the problem. Most real-world models use nonlinear activations like sigmoid, tanh, or swish. These functions lack the clean structure of ReLU. Their non-convex, smooth nature makes them extremely difficult to encode in traditional verification frameworks. As a result, many approaches resort to conservative approximations, over-approximating the reachable output set to preserve soundness. But this comes at a cost. Completeness is lost. The method might miss valid adversarial examples, or worse, fail to certify robustness even when it exists. This trade-off between soundness and completeness has long been a bottleneck in formal verification. Until now, our work introduces a new paradigm: quantum-optimized robust verification, combining the power of quantum-inspired computing with deep mathematical insight to address this challenge head-on. We propose two novel models. The first, for piecewise linear activations, like ReLU and hardtanh, delivers exact, sound, and complete verification. It transforms the verification problem into a quantum-amenable optimization formulation that preserves the full structure of the network's behavior. No approximations, no false negatives, just precise, provable guarantees. The second model extends to arbitrary nonlinear activation functions, including sigmoid, tanh, and beyond. Here, we introduce a novel framework based on piecewise-constant bounds. While this is an over-approximation, it's not just any approximation, it's asymptotically complete. As we refine the segmentation of the activation function, by increasing the number of discrete intervals, the approximation error vanishes. In the limit, it converges to the true reachable set. This is a significant theoretical advance. We now have a scalable, provably tight method for verifying networks with complex, nonlinear dynamics. How do we solve these problems efficiently? We integrate quantum Bender's decomposition with interval arithmetic. Interval arithmetic preprocesses the network to estimate feasible ranges for each neuron's preactivation. This allows us to prune infeasible segments, removing entire branches of the search space before even touching the optimizer. This dramatically reduces the number of binary variables, a critical step given current hardware limitations. Then we use Bender's decomposition to split the problem into two parts: a master problem that handles discrete activation patterns via binary variables, and subproblems that solve for continuous bounds. This decomposition enables a quantum classical hybrid workflow, where the combinatorial, discrete decisions are offloaded to a quantum processor, while the continuous verification remains classical. But here's the key innovation: certificate transfer from pruned models. Pruning removes parameters and reduces dynamic range, making the network easier to verify. We prove that if a pruned network is verified, we can transfer the robustness guarantee to the original model with quantifiable bounds. This allows us to use smaller, faster verification runs to certify larger, more complex models, effectively turning pruning into a verification accelerator. To scale even further, we introduce layer-wise partitioning. Instead of encoding the entire network into a single quantum problem, something that quickly exceeds the spin budget of current Ising machines, we split the network. The prefix early layers is handled classically using interval or linear relaxation bounds. The suffix later layers is verified on quantum hardware using our QUBO formulation. This hybrid strategy maintains correctness while drastically reducing the number of spins required. Now let's talk about results. We evaluated our framework on 3 benchmark datasets: Iris, Make Moons, and MNIST-like synthetic tasks. For ReLU and hardtanh networks, our global QUBO formulation achieved perfect agreement with the QUBO baseline, identifying the exact same number of vulnerable samples across all perturbation budgets. But unlike classical solvers, our QUBO formulation is solvable on quantum-inspired hardware. On a coherent Ising machine, CIM, the CIM solved problems that exceeded the 5-second timeout of QUBO, finding adversarial examples in cases where the classical solver failed. And crucially, the number of spins required was manageable, growing only moderately with perturbation size. For sigmoid networks, the results were even more striking. Despite using a coarse 5-segment piecewise-constant approximation, our method matched the MIP baseline in adversarial sample detection, with only a 1-sample deviation at the largest perturbation. Meanwhile, the average number of Ising spins remained under 100, a fraction of what's needed for ReLU networks. When we applied the Bender's decomposition framework to larger networks, the results were near perfect. Certified accuracy matched the exact MIP baseline across all activation types, ReLU, hardtanh, and sigmoid, demonstrating that the decomposition preserves correctness while enabling scalability. This isn't about beating classical solvers in wall clock time. It's about establishing a new principle. Quantum optimization can serve as a principled, scalable, and mathematically rigorous primitive for robustness verification. Our framework is modular and solver-agnostic. As quantum hardware evolves, more spins, better coherence, lower noise, the performance will only improve. The pipeline is designed to scale with the technology. In summary, we've bridged the gap between theoretical robustness and practical verification. By combining exact formulations for piecewise linear functions, asymptotically complete approximations for general nonlinearities, quantum Bender's decomposition, interval pruning, certificate transfer, and layer-wise partitioning, we've built a unified end-to-end system that is both correct and scalable. This is not just a new algorithm. It's a new verification paradigm, one that leverages quantum optimization not as a magic bullet, but as a structured, principled tool for building trustworthy AI. The future of safety-critical AI isn't just better models. It's better guarantees. And now, with quantum-optimized verification, we're one step closer to making that future real.